Hello and welcome to the fifth lecture of Advanced Material Chemistry, Advanced Functional Materials Part 2. And in this lecture, we are going to see thermoelectric devices. Before that, let us see what we learned in last lectures. So we know that almost all the practical devices are made using semiconductor materials. This is very clear to us by now. And then we saw solar cells and learned that solar cells are basically PN junction based devices, and these devices converts light into electrical energy. Photovoltaic technologies can be categorized into three generations. In the first generation, there were solar cells based on single crystals or polycrystalline materials, basically wafer based. Then second generation solar cells were based on thin film based technologies. Then comes polymer solar cells, bilayer solar cells, bulk heterojunctions, nanostructured bulk heterojunction solar cells, dye sensitized solar cells, solid state dye sensitized solar cells, perovskite and quantum dot solar cells. So these solar cells and some other new kind of devices, they comes under the third generation of the solar cells. These solar cells we studied in details. All of them by now we have understood very well. Now let us come to another kind of power generator generation devices, that is thermoelectricity. Let us first learn what is the fundamental of thermoelectricity. So first let us consider a metal piece. Suppose this is a metal piece. So in metal we know that there are free electrons. Why there are free electrons? Because the valence band and conduction band overlaps, and at any temperature above 0 Kelvin, there is certain thermal excitation, and because of those, the valence band electrons moves into the conduction band. And since the electrons in conduction band are they belongs to entire crystal, so we consider them as free electrons, though they are inside crystal only. Whether at 0 Kelvin we can have free electrons? Ideally no, because at 0 Kelvin all the electrons will be bound to their parent atoms. Now as the lattice is also not vibrating, they are also, all the atoms are at rest, so in the metal there will not be any free electron at 0 Kelvin. But as the temperature increases, the electron moves into conduction band, and we consider these as a free electron for practical purposes. So this is a metal. Now we consider that all the electrons are uniformly distributed throughout the metal. Now just imagine we start heating this metal plate from one end. Now what will happen? Because we will heat it, so the temperature of this side will start rising, and after a certain time a temperature gradient will be established. So this end will be at particular temperature and another end will be at a lower temperature. So there will be a temperature difference T1, T2 and a gradient. What will be the gradient? Gradient is T1 minus T2 divided by the length of this metal. So now as the temperature of this side is increasing, so the electrons they will start gaining the thermal energy. And because these electrons are having now more thermal energy, they will try to move from this side, and after certain period of time, you will see that electrons have moved from this side to this side. All the electrons will not move, but you can say there will be a relatively uh, more electrons in this side and less electrons at this side. This is only for pictorial purpose, so it shows that all electrons have moved, but there will be electrons here also. So now the charge has moved, electrons are having negative charge. So you will see this end will have slightly negative potential as compared to this end. So this will be positive compared to this end. Now if you try to measure the potential difference between these two, it will be V2 minus V1. Suppose this is a V2 potential, this is V1 potential. So because of thermal gradient, the motion of electrons from one side to another side has actually created a potential. This is an important concept. So temperature gradient is applied across a metal or semiconductor also, and therefore the charge carriers can be electrons or holes also in p-type. They diffuse from hot end to cold end. And because of this diffusion or movement, a potential difference builds up between these two ends. So this is how much V2 minus V1. So now if you see, if you start, means they are at constant temperature. So whether the electrons which are actually gaining energy here, they will continuously, all of them will go on moving this side. See, after a certain time, what will happen? This side has become negative and this side has become positive. So now further movement of electrons will be stopped because this negative potential will repel them. So at a constant temperature and after a certain time, a thermal equilibrium will be established, where this end will be at a fixed potential V2 and this end will be at a fixed potential V1. So now we applied a temperature gradient, and because of the temperature gradient, the charge carriers move from one side to another side. Because of the movement of this charge, a potential is established, and because a potential is established, this potential further resists the movement of charges from one side to another side or in the same side. So in thermal equilibrium or in overall equilibrium, you see a constant potential is developed between these two ends. Now, just imagine this was a metal piece. Now we have taken two metal pieces. It's the same metal, and we have just make a joint at one place, and the other side is open. And this end we start heating. We put this part exactly below this candle. So the temperature of this will start increasing. Electrons will move from this side to this side. A potential will be generated. So this will be at V2. This will also be a V2 because it is a you can say identical metal. So if we have an identical metal and we make this kind of joint and heat one end and try to measure the potential difference here, it will be zero because both these ends will be exactly at the same potential. So suppose I consider the same metal here. So this will be at V2, this will also be at V2. So if I try to measure the potential difference between these two points, it will be zero. So in that case, it will not be of any use to us as far as thermoelectric devices is concerned. Now let us just change the one metal to some other metal. Now, if we add two dissimilar metals and they are joined at one end here and heated up to a temperature which is higher at this point, suppose we say TH, the other end of both metals are kept at the constant same temperature, that is constant, it will be room temperature or any other reference temperature, can be 0 degree centigrade also. Let us consider is Tc here. The potential difference or electromotive force built up between those two metals. Why? Because every metal has a property the motion of electrons, the generation of EMF, that will depend on material. Suppose you have copper, it will have a different potential difference, and if you have some other metal, silver, so you will have a different potential difference. So now suppose you try to measure put a voltmeter, a highly sensitive voltmeter, because this is very low voltage, then you can measure the difference between these two points. So now what you have gained, a temperature gradient has been established between these two ends, and accordingly a potential has been generated. So this delta T has generated this potential delta V. So the temperature difference can be converted now into a potential difference, and this is called as Seebeck effect. So now we define a coefficient which is called as Seebeck coefficient, which is the value of delta V, means how much voltage has been generated, divided by delta T, how much temperature gradient you have applied. So Seebeck coefficient is the voltage generator or voltage difference generated per unit temperature difference. This is clear. So now if it is clear, then everything of thermoelectric devices should be clear. Now we have to just see different strategies. Now if we join, this was actually metals. If we join one p-type and n-type semiconductor, suppose this is a p-type semiconductor and this we have an n-type semiconductor, what will happen? The electrons and holes in p-type, holes will move to other side. In n-type, electrons will move. So you will have, actually you will get more the potential difference, because in if both are metals, in that case what you are gaining, both are at negative potential but slightly different to each other. However, if you have a semiconductor and one is p-type, another is n-type, so your potential will be enhanced, potential difference will be enhanced between those two pooled junctions. So the performance of a thermoelectric devices depends on figure of merit. So this is clear, the thermoelectric method. Now the performance of this device, it depends on figure of merit. We define something called as figure of merit, and it is of particular materials. For any material you have certain ZT. If you change the material, you will have different ZT. And how we define it is alpha square sigma divided by K and T multiplied by T. T is absolute temperature. So where alpha is Seebeck coefficient, sigma is electrical conductivity, K is thermal conductivity. Thermal conductivity has two components. One is electronic component and another is lattice component. So this comprises of two parts. And if you want to use if you want to commercialize some thermoelectric devices, then in general, if ZT is greater than 2, this is considered as a reasonable thermoelectric material. for device applications. In the conventional materials, the ZT value of ZT is nearly 1. So now by seeing this, the more the figure of merit, better is the thermoelectric material. Now what we should have? We should have more electrical conductivity, more Seebeck coefficient, more electrical conductivity, and less thermal conductivity at a particular temperature. So high Seebeck coefficient, high electrical conductivity, and low thermal conductivity. But we know that thermal conductivity and electrical conductivities are related. If a thermoelectric material with figure of merit ZT is operated between hot end and at temperature, suppose consider TH, and cold end temperature, let us consider TC, then in ideal situation, we can find out the efficiency, which is equal to TH minus TC divided by TH. TH is temperature of hot end, and then square root 1 plus ZT minus 1, then square root 1 plus ZT plus TC by TH. A typical efficiency of thermoelectric generator is 5 to 8%. However, some good thermoelectric materials can give you about 10% efficiency also, but they are not commercialized yet. So by seeing this, if we want to make a thermoelectric generator, so we have a hot end and then we have a cold end. And between these hot end and cold end, we put our TEG. TEG is what? It is nothing, but you consider the assembly. For time being, you just imagine two dissimilar materials added, joint at one end and open at another end. So that also you can just imagine it is a thermoelectric generator. So hot end, cold end, and this entire thermoelectric device has been put between hot and cold end, and then across this you can have connections, and then an external load through which the current flows. So current is generated in this TEG device and it flows through this external load. This is clear. So working of thermoelectric generator is based on Seebeck effect. Thermoelectric power generator is a solid state device that converts heat directly into electricity. It consists of heat source, which is kept high temperature, and heat sink, which is maintained at a temperature less than the heat source. The temperature difference between heat source and heat sinks causes direct current to flow through the load. Now, what kind of current it is? As in solar cells also we have direct current, and here also we will have direct current only. However, in our domestic uses, we use alternating current at 50 Hertz frequency. So if we want to use it in our for our appliances, in that case, this DC has to be converted to AC. Now, you see this TEG device, in order to have higher ZT value, it should have a good electrical conductivity. However, at the same time, it should have a low thermal conductivity. Why it should have a low thermal conductivity? Because if the conductivity is high, then after some time, what happens? This entire device will be at the same temperature, and it will be very difficult to maintain the temperature gradient. For example, you have a very good thermal conductor, and you put between a hot end and cold end, and so the heat will be transferred from hot end to cold end, and the temperature of cold end will start increasing, and it will be very, very difficult to maintain this temperature gradient. Therefore, the thermal conductivity should be low. However, electrical conductivity should be very high. This is a just operation of a thermoelectric generator. So suppose you have a heat source, some heater is here, and you have a heat sink, something like you have maintained that at a low temperature. Suppose at connected to some water reservoir at 30 degrees centigrade or some ice at 0 degrees centigrade. Now, the electrons and holes in p-type electron holes will move, in n-type electrons will move, they will move to this, they will be collected here, and then after that through the external circuit they will move through this load and the current will flow. Just see once again. So now this is a typical thermoelectric generator where an n-type and p-type materials are joined together. That helps to add the potential or increase the potential, and at the same time you can join many such devices in parallel to increase the current. So a typical thermoelectric generator is same, hot and cold end. In n-type, electrons flows, in p-type, holes flows from here. So you get holes here, electrons here, and they go through the external circuit and through this load. So the power generated due to Seebeck effect is a single phase DC and given by I square RL. The power is always V into I into R. Now here we are having current, so it is I square RL, and RL is load resistance. The output voltage and output power are increased either by increasing the temperature difference between the hot and cold end, or by connecting several thermoelectric power generators in series. So suppose now you want to increase the power. What you can do? One thing you can do, you can increase the temperature. If you increase the temperature, delta T will increase. If delta T will increase, the potential will automatically increase because Seebeck coefficient of this material is constant. So as you increase the temperature difference, the potential difference will increase. The voltage of this generator is given by V is equal to alpha into delta T, where alpha is the Seebeck coefficient and delta is the temperature difference between these two ends. All thermoelectric power generators have the same basic configuration as we have shown in this figure. Now, if we want to combine many such small thermoelectric units, we get the this kind of modules. So in it, and this kind of modules are called as cascaded devices. So in the thermoelectric cascaded devices, P and N type materials are connected electrically in series and thermally in parallel. Thermally in parallel means see all one end is connected to the hot side of the temperature source, and another is all the other side is connected to the colder side, and the colder side connections are actually connected in series so that you can increase the power. So in thermoelectric device module, where when operated between a hot and cold end, it can convert the heat energy to electricity, as I already said in earlier slides. In this way, thermoelectric coupled module can be used as a power generator. So you can see here, these are thermally in parallel. However, they are electrically in the series. See, you see this way, they are in the series, and thermally all the, you can say here, you can see one will go to hot end, another will go to, another side will go to the cold end. Now, if we have a semiconductor material, the Seebeck coefficient is related to the different parameters by this formula: 8 pi square m star k square t 3 e h square and pi over 3n to the power 2 by 3. M is the effective mass. You remember the effective mass? We studied the concept of effective mass in the first lecture. K is Boltzmann constant, T is temperature in Kelvin, E is charge, and H is Planck's constant. And N is the carrier concentration. Now let us understand these two conductivities, which are electrical and thermal conductivity. So the electrical conductivity we all know from our basic physics, that electrical conductivity and electrical resistivity, they are related to the carrier concentration and the mobility. So you have this is your conductivity, this is your conductivity, and this is your resistivity. Resistivity is 1 over conductivity, reciprocal of the conductivity, and equal to carrier concentration, charge, and the mobility. However, the thermal conductivity is the property of a material which indicates its ability to conduct heat. Thermal energy can be transported by any type of excitations in a solid. In our case, we are mainly interested in two types of contributions. What are those two types of contributions? See, heat is transported from one place to another place in any material by two ways. Number one is, as we saw earlier, the electrons which have gained energy, they can transport that energy from one side to another side. So that is the electronic contribution. And then another contribution is the thermal contribution, the lattice contribution. What happens in the crystal, as you start raising the temperature, the lattice start vibrating. And can it vibrate with all possible frequencies or all possible amplitude? No, that also we saw that this vibration is also quantized. However, this energy, this whatever energy it is actually oscillating with, or whatever energy it is having, it can travel through the lattice in form of phonons. As we have photon in case of electromagnetic radiation, here we have phonon. So as we, if you can recall, there was we saw that atom was vibrating, and it can have one energy, vibrating energy, or you can say one amplitude. Then it can have another amplitude which is quantized. So if it has to move from one state to another state, it has to absorb certain amount of a fixed quanta of the energy, and that quanta of the energy is in terms of phonons. So therefore the phonon absorption and emission, that provides these thermal vibrations, change in the thermal vibrations. So now if one atom is vibrating and there is another atom which is coupled, that is also vibrating, this energy, it can it is also vibrating. So if it is changing the energy, it will emit an phonon. This phonon will go and it will be either absorbed or move ahead. So the phonon, these phonons travels through the lattice. So now we see two thermal conductivities. The lattice thermal conductivity, it can be given by this formula 1/3 C and then L and then V. C is the specific heat at constant volume. L is the mean free path of the phonon. So phonon, if it is emitted from like one vibration and before it is absorbed or is strike to another lattice, vibrating lattice, it has a mean free, it has a certain free path, that is mean free path, and V is the average velocity of the phonon which is moving. And this mean free path is determined by phonon-phonon scattering or phonon impurity scattering. Then the other one, which was the electronic thermal conductivity, that is having a formula of L into sigma into T, where sigma we know it is E NE mu, and then LT, and L is Lorentz vector. This is typically for free electrons, 2.4 10 to the minus 8. The Lorentz vector changes for electrons in a single parabolic band and multi-parabolic bands, and has to be determined carefully for different materials. So this value of L is different for different materials. At higher temperatures, due to excitations of electrons, the electronic contribution becomes large, and this value of this electronic contribution can be extracted from the total. You see how do you suppose you want to find out the electronic contribution. In that case, there is no direct way to find out. So first thing is that you can calculate the total thermal conductivity, which is very easy. You can have a general formula dq is equal to ka dt by dx, and then you can find out the lattice contribution, and then you can subtract the lattice contribution from the total, and you can find out the electronic contribution. Now suppose you want to select good thermoelectric materials. So first thing is that the carrier density. Carrier density means number of electrons present in that material, or holes. Holes also in p-type materials. So optimum carrier density is 10 to the power 19 per centimeter cube. And this comes 10 to the power 19 is corresponding to heavily doped semiconductors. If you recall, it maximizes the power factor because it is, we can say, sigma square. There is a rule for this finding out this, that is 10 kb 10 k beta T rule, and it says that band gap of the material should be equivalent to 10 kT, where the T is the operating temperature, and K beta is the constant. So reasoning behind this is that small gaps are generally good for thermoelectric performances, as they lead to higher carrier mobility. If the gap is large, the carrier mobility will be low. However, if the band gap is too small, then the thermal excitations of the minority carriers will adversely affect, because electrons and holes carry heat in opposite directions. So if the you can say gap is low, in that case, because of the thermal excitations, electron will anyway move to the conduction band. Another thing is the electronegativity difference, which is a measure of the covalence of the bonding in the material. Large electronegativity difference indicates ionic bonding, large charge transfer, and strong scattering of electrons by optical photons. These large scattering causes low carrier mobility. Therefore, a good thermoelectric materials are composed of the elements having small electronegativity difference. A good thermoelectric material will have large average mass, as heavy atoms corresponds to low thermal conductivity due to the small acoustic phonon generating. If the atom is very heavy, it is going to vibrate lesser. Then mass fluctuation scattering, because of the change in these masses, can be used to reduce the lattice thermal conductivity. And crystal structure with many atoms tends to have low lattice thermal conductivity. One of the argument is that the number of defects per unit tend to grow as the size of the cells increases, and that causes it to be a region of low thermal conductivity. Crystal structures that have highly coordinated ions, these tends to have lower thermal conductivity. However, this is just an empirical relation. So if we try to see here, so if we like here on the x-axis we have carrier concentration. So you see if the carrier concentration, this side it is low, this side it is high, 10 to the power 21. Typical concentration is this which is used. So as we try to increase the concentration, what will happen? More the number of electrons are there or more the number of carriers are there, the conductivity will increase. So conductivity is directly proportional to the number of carriers. So this is the conductivity. So it is alpha. Alpha is, you can see, increasing linearly as the concentration is increasing. If you multiply this, sorry, it is sigma, not alpha. So if you multiply, the sigma is increasing as the concentration is increasing, and the alpha, the value of alpha is decreasing as the number of electrons are increasing. So if you multiply alpha square into sigma, you get this kind of curve. So this curve will give you and the electrical part. Now if you see for the thermal conductivity, you can see that it has two parts. One is the lattice part. Lattice part is, it doesn't depend on the carrier concentration of electrons. So you have a constant KL here. And as the number of carriers are increasing, in that case, what will happen? That will also increase because that is proportional to E. So now you add both these and you will get a curve which is approximately this. So the power factor, which is this much, and the dimension figure of merit ZT is alpha square sigma. So this is alpha square sigma and divided by K, this total K, this is Ke plus KL, and then T. So it can be maximized at carrier concentration of 10 to the power 19. So if you multiply these, then you will get a value of ZT. So you can see the ZT, if you plot, it will come like this. You multiply this, and then these things, and then you will get a curve like this. So at nearly 10 to the power 19 carrier concentration, you get the maximum ZT value. Therefore, this is an optimized concentration, which is 10 to the power 19 and is best suited for good thermoelectric material. Now this figure of merit, as we saw earlier, the figure of merit is directly related to the efficiency of thermoelectric generators. So if we plot with the temperature difference, that is delta T. So, and this is the device efficiency. So for different ZT values, so if ZT value is 1, then you see the efficiency is low. If ZT value is more and more and more, then accordingly the efficiency is going to increase. So if for a temperature difference of 500 degrees centigrade, the ZT value of the material is suppose 10, then you will get an efficiency of nearly 34%. These are different kind of materials which are used in thermoelectric devices. So P-type material, these are P-type materials like bismuth telluride, P-type bismuth telluride. You have bismuth telluride N-type also by doping. These are by different dopings. Then you have different materials. So you can see the ZT values for like this material, the ZT value is very high at low temperatures. Similarly, if these materials, the ZT value is high compared to here at relatively higher temperature. So it depends in what temperature range you want to the material. You want to use your device, and accordingly you can choose the material. So suppose up to 200 degrees centigrade, you want to make it thermoelectric devices where the temperature of the source is nearly 200 degrees centigrade. You can very simply use Bi2T3, Te3, and if you want to use at a slightly higher temperature, maybe up to 500 degrees centigrade, then you have lead telluride and TAGS, which is actually a alloy of different metals, and this can be used up to 500 degrees centigrade. And then if you want to use at even higher temperatures, suppose 800 or even more, in that case silicon germanium is the base material. So for temperatures nearly 1000 degree, you go for silicon germanium and all. So now as we can see that we require higher alpha and higher sigma. See, ZT is alpha, which is Seebeck coefficient, sigma, which is our electrical conductivity, and K is thermal conductivity. So we require upper side should be more, and this denominator side should be less. So we require higher alpha, we require higher sigma, and we require low K. So material with these type of properties are rare in nature, because the material which is having high thermal conductivity or high electrical conductivity is generally have higher thermal conductivity also. So because electrical conductivity and thermal conductivity are somewhere correlated. So we have to make certain efforts, or we have to devise some methodologies where we can increase, or you can say we can increase the thermal conductivity, decrease the thermal conductivity by maintaining the electrical conductivity. So metal have very high electrical conductivity, but very low Seebeck coefficient and very high thermal conductivity. Whereas glasses have very low thermal conductivity, but at the same time they obviously has low electrical conductivity also. So a concept was proposed for like making materials which will show low K as in glass, but high sigma, as well as in ordered crystal, in well-ordered crystals. This is also known as PGCE, or phonon glass electron crystal. What is PGCE? PGCE is a phonon glass electron crystal, and this is having low thermal conductivity. However, it is having high electrical conductivity. To control these properties as we wish, it is very difficult, and because as we have already discussed that they are interdependent. So in recent times, this problem is attacked in two different fronts. What was those two fronts? Synthesis of new materials in solid solution. So solution of two different solids which has very complex crystal structure and thus very low thermal conductivity. So if the structure is different, they are very complex actually, so they will have low thermal conductivity. And using material in a nanostructured form, which will enhance the ZT. So if the material is nanostructures, means you have made the structure is of the nano level. In that case, the phonon contribution can be reduced. So the idea is lower structured, 0D, so there is no possibility 1D or 2D materials. This shows high electrical properties far beyond the reported in the bulb. So there are three generation materials. First is in the first generation kind of materials, the strategies for improving ZT were like point defect scattering, and this creating point defects inside the material deliberately. And this what these point defects does, they are the source of scattering the phonons, and therefore they will reduce the thermal conductivity. And the N, which is the carrier concentration, it is optimized. You can increase it. Then alpha square and sigma, they will increase. So this, you increase the conductivity by optimizing the carrier concentration. At the same time, you create point defects inside your material deliberately, and it reduces the thermal conductivity because of phonon scattering. So these kind of materials are called as our first generation materials. Then after little advancement, there was nanostructuring, and this nanostructuring has reduced the thermal conductivity. And these kind of materials, by like nanostructuring, one could attain the ZT values of 1.3 to 1.7 range. Then there is third generation materials. In the third generation materials, the ZT values are more than 1.8, and these are having, in addition to these two, there introduction of mesoscale structuring, and this mesoscale structuring reduces the thermal conductivity. And also the doping induced electronic structure modification, and this electronic structure modification, you create additional levels, and it actually enhance the the sigma, and then obviously alpha square sigma also. And then matrix precipitate band alignment, and this also reduces the thermal conductivity. And by doing this, the alpha square sigma, or the electrical conductivity remains constant. So therefore, by like introducing point defects, you can say by introducing point defects for in bismuth telluride, the lattice constant, which was actually the lattice conductivity, thermal lattice conductivity, which was 2.4 watt per meter per K, and ZT was about 0.6 for these bismuth, antimony telluride, and bismuth telluride, tellurium, and selenium. These have lattice conductivity of about 1.5, and ZT of the value which is very close to 1. Then you can have increase the lattice period, which is large unit cell parameters. How do you increase the lattice period? Basically making the crystal which having larger ABC values, and these provide the short mean path length. And by using boundary scattering, the material grind and make pellets using hot pressing, and by nanostructuring. So to summarize this part, the thermoelectric part, the most commonly used material for this generator is lead telluride. Lead telluride is compound made of lead and tellurium having small amount of bismuth or sodium. Other compounds used for making thermoelectric power generators are TAGS. TAGS is an alloy of tellurium, antimony, germanium, and silver. Bismuth telluride, bismuth sulfide, germanium telluride, zinc antimonide, zinc telluride, and indium arsenide, etc. The applications of thermoelectric generators are for increasing the fuel efficiency of cars. Thermoelectric generators are used. The car has certain engine which is very hot, so you can put a thermoelectric generator there, so that heat which otherwise goes waste can be utilized in power generation. Similarly, at the silencer part also, which is also very hot, you can put a thermoelectric generator there and generate the power when your vehicle is running. Then seabed power generation is used to supply power to spacecrafts in deep space missions. When your spacecraft goes to deep space mission, means very deep in the space where the sunlight is not reaching. Normally, if you have a spacecraft uh, up to a place where the solar energy is available, you can use solar cells. But in deep space, where sunlight is not there, you cannot use the solar cells. So for those kind of applications in deep space missions, you require the thermoelectric power generators. So for that, the entire power generator is having a heat source and the TEG, and then cool is anyway outside is at nearly 0 K in space. So you have hot end where you are providing a heater kind of thing that can be any source of heat. Normally, the radioisotopes are there. These generators are used to supply power to remote stations also, like in solar cells. Certain advantages for thermoelectric generators as an alternative source of energy for special applications such as deep space missions, as I already said, remote inaccessible locations requiring no maintenance replacement. You can use, once you have established a TEG device which is giving power, and you have fixed a heat source, and that heat source is at a constant temperature. In that case, you don't require any maintenance or replacement, because they are very robust. Materials are robust materials. Harvesting heat emitted by human body, instruments, automobile industries. So, your body temperature is also about nearly 33 degrees centigrade. So you can have certain thermoelectric devices which works at this temperature range, and then though it will generate a very low power, but some devices like modern days electronic devices, they require a power in microwatts. Such kind of powers can be generated by utilizing human body heat only. These devices have certain limitations also. First thing is high output resistance. These devices generate high current but very low voltage. The typical for like a very good thermoelectric generator using two metals, the difference is the Seebeck coefficient value is in the 10 to the power minus 6 range. So you can see about 100 degrees centigrade temperature difference will generate only a few microvolt of the you can say potential difference. So for getting high output voltage and power, several thermoelectric generators are connected in series. Suppose you want 1 millivolt. In that case, and your one device is giving 10 microvolt. In that case, you need to add 100 such devices in series. So if you go on adding such devices, your series resistance will increase. So that will increase the resistance, and because of the resistance is increased, the efficiency will come down. And then thermoelectric power generators generate less electrical power for the same heat flows. That is, they have low efficiency if as compared to other mechanical generators. Low thermal characteristics. The heat dissipation of any device depends upon its thermal conductivity. Any good thermoelectric power generator has low thermal conductivity and hence poor heat dissipation. So these generators are efficient only when small power is required. Thermoelectric generators are costly as compared to other generators. I think with this we have covered the thermoelectric part. Now let us see Peltier effect. So Peltier effect in a very simple way, it is actually opposite to the Seebeck effect. If two dissimilar metals are joined together at both the ends, a current is flown, then at one end heat energy gets rejected and at another end heat energy get absorbed. So earlier what was there, you have one device where one end was at higher temperature, another end was at lower temperature, and then a current was flowing through that junction or through the entire closed loop. Now, if you have they are not at different temperature, but they are at the same temperature, but materials are dissimilar, and you start flowing current through this kind of junction, then at one junction the heat will be absorbed, and at another junction the heat will be evolved. This effect is called as the Peltier effect. It is opposite to Seebeck effect. If the charge carriers are going from the low Fermi energy, so suppose this is the low Fermi, now you have joined two materials. One is this, another is this. So this is here you can see this is valence band, this is conduction band, this is similarly valence band, conduction band. So Fermi level here is low. So if the charge carriers are going from low Fermi energy side to high side, then the required energy will be supplied by the lattice. And because the lattice is actually supplying the energy, so it will get cooled. However, in the other junction, when it is moving from higher to lower one, in that case, the energy will be released, and that energy will be in the form of heat. So at one junction, you will eject heat. At the another junction, you will absorb the heat. So now, if this process continues, you keep on flowing the current for a very long time. In that case, one end will become hot and another end will become cold. So these Peltier devices are used for cooling. So this is a Q Peltier is defined as this, and this is called as the Peltier coefficient for any thermocouple. Thermocouple is when you join two dissimilar material, and these are used for measurement of the temperature. Now comes the Thomson effect. Suppose you have a material in which you have already established a temperature gradient, and if you start passing a current, so when a current is passed through a conductor, semiconductor, which is already having a temperature gradient, then heat is either evolved or absorbed. This phenomenon is called as the Thomson effect. So suppose you have a material in which a temperature gradient is established, material is same. In the Peltier effect, there are two dissimilar material. Now you are having one material only, but this material is having a temperature gradient. Temperature gradient is established by heating one end and or removing heat from the another end. So one is at hot, another is at cold temperature. So if a current is passing through this material, which is already having a temperature gradient. In that case, heat is either evolved or absorbed. And this is called as the Thomson effect. If 2 points in a conductor are at different temperatures, the density of electrons at these points will differ, and as a result, the potential difference is created between these points. If current is passed through a copper bar, suppose this is a copper bar, if suppose this is copper bar, suppose the current is passing through this and we have heated this at the center. So this will be at like higher potential. So when an electron is moving from this side to this side, the heat will be absorbed from A to C, and heat will be evolved from C to B, because this is at the higher temperature. So potential is also high here, and current is actually opposite to the movement of electrons. So this indicates that heat is absorbed along AC and evolved along CB of the conductor. Thus, heat is transferred due to current flow in the direction of the current. If heat is transferred because of the flow of the current and in the same direction of the current, then it is called as a positive Thomson coefficient, positive Thomson effect. Copper, silver, zinc, and cadmium have positive Thomson coefficient, and the Thomson coefficient is defined as by this tau. It is 1 by I dq by dx, and then you divide it by temperature gradient, or this value per unit temperature gradient. So, like if we summarize all this thermoelectric part, then the thermoelectric defect is the direct conversion of temperature difference to electric voltage and vice versa. Traditionally, term thermoelectric effect or thermoelectricity encompasses three separately identified effects. One is Seebeck effect, another is Peltier effect, and the third one is Thomson effect. The Peltier and Seebeck effects are the most basic of these three effects and are essentially the inverse of each other, for which reason the thermoelectric effect may also be called as Peltier-Seebeck effect. Because the materials are same, so if you start supplying or you start passing the current, then it will be Peltier. If you put them with a temperature gradient, then this will call as the Seebeck effect. Then Joule heating. What is Joule heating? When you pass a current and because of the resistance, the temperature is increased. That is different. That is not actually thermoelectric. That is not a Peltier effect. So Joule heating, the heat is generated when a voltage difference is applied across a resistive material. It looks same, but it is different. It is totally different than thermoelectric effect. The Peltier, Seebeck, and Thomson effect are reversible, where Joule heating is not reversible. So if you have a resistance, if you start cooling it, it will not give you any current. That means this. A thermoelectric device creates a voltage when there is a different temperature on each side, and when a voltage is applied to it. It creates temperature difference, and this can be used to generate electricity, to measure temperature, to cool objects, or to heat them. This is the present status of thermoelectrics. In like inorganic semiconductors, if you see for like bulk devices which can be segmented to improve, the highest ZT is nearly 3.1, and it is at 783 degree 83 Kelvin. And for these materials are used polycrystalline P-type, tin, selenium, and the efficiency of this is 12%. And efficiency not actually this efficiency of these materials is nearly 12% in the segmented devices. And for like organic conducting polymer based thermoelectric materials, for flexible devices, they are showing very poor ZT. They are actually not very stable, and high conductivity N type material is also an issue. It is not available. So the highest ZT for organic is nearly 0.42 at room temperature, and this is for PDOT PSS thin film. In BARC also we are doing work in thermoelectric power generators. So these are typical generators developed in our division at thermoelectric group in our division. So these are in three different temperature range from 100 to 300 degrees centigrade, where the hot side is at 300 degrees centigrade and cold side is 400 degrees centigrade. This is the material which is used, and a typical efficiency of 6.3% is achieved. For mid temperature ranges, where the one side is kept at 550 degrees centigrade, lead telluride and TAGS 85. This is the you can say one leg is PBTE and another is TAGS, and with this an efficiency of approximately 6% has been achieved, and it can give you about 450 milliwatt of the power. In the case of segmented leg thermoelectrics, the temperature, the hot end temperature is 520 degrees centigrade, cold end is 33 degrees centigrade, and the efficiency of nearly 12% has been achieved. So this completes the thermoelectric generators. Peltier effect, Thomson effect, and different methodologies to make thermoelectric devices. Now we come to the part 3 of this syllabus, which is device-worthy materials, important elemental and compound semiconductors, which are germanium, silicon, tellurium, second, sixth element, third, fifth element, similarly fourth, sixth element, and amorphous silicon. And the other is silicon crystal growth and techniques, Czachowski method, float zone method, hydrothermal growth methods, single crystal growth of silicon and gallium arsenide, production process of wafers, growth of quartz, and thin film deposition techniques, thermal and electron gun evaporation, DC and RF sputtering. These two parts we will see in the next lecture, and today, because this is a small part, we will try to finish it very quickly. So important elemental and compound semiconductors, mostly whatever we are going to see now, we have already covered in the first lectures. So group 4 elements compounds, these are silicon. This is an elemental semiconductor, germanium, that is also elemental semiconductor. And then compound semiconductor of group 4 is silicon carbide. Then if we see important semiconductors of compound semiconductors of group 4-6, these are lead sulfide, lead selenide, lead telluride. We come to silicon. Silicon is an important material used in the semiconductor industry very widely, and it has a melting point of 1440 degrees centigrade. The boiling point is 3265 degrees centigrade. The density is reasonably low, 2.32 gram per centimeter cube. The crystal structure is face-centered cubic. Face-centered cubic, it is actually diamond structure. So diamond structure is face-centered cubic structure with the basis having atom at 0, 0, 0 and 1 by 4, 1 by 4, 1 by 4. The thermal conductivity is 149 watt per meter K. Electrical resistivity is 2.3 into 10 to the power 3 ohm meter. Band gap is 1.12 electron volt. Thermal expansion is 2.6 micrometer per millikelvin. The production, silicon up to 99% purity is made by reducing sand with highly pure coke. The reduction is carried out in an electric arc furnace. Excess silicon dioxide is used to stop accumulation of silicon carbide. So silicon is produced that is from sand. So you have SiO2 that is reacting with carbon. It gives you Si plus CO, and then this SiC and SiO2 that also gives you silicon and CO. Similarly, another elemental semiconductor, that is germanium. The melting point is 937, boiling point is 2830 degrees centigrade. This is band gap. The electrical resistivity is this. The crystal structure is same, diamond. Density is high as compared to silicon. The thermal expansion is 6. The thermal conductivity is 60.2, and this is a very widely used semiconductor after silicon. Reacts with oxygen at higher temperature and makes germanium dioxide. The physical properties, it's a bright, sunny and brittle. The chemical properties, it is inactive, does not dissolve with water or react with oxygen at room temperature. It is produced mainly from spherite. Spherite, that is an ore of germanium, zinc, sulfide. It is also found in silver, lead and copper ores. Another source of germanium is fly ash of power plants fueled from coal deposits that contains germanium. Then comes amorphous silicon. Amorphous silicon is the non-crystalline form of silicon used in TFT and LCD and solar cells. In amorphous silicon, not all the atoms are four-fold coordinated and no long-range order is present. Some atoms have dangling bonds, which represents defects, which leads to anomalous electrical behavior. It is passivated by hydrogen, which makes a bond at the dangling bond site and reduce their density by several order of magnitude, the density of dangling bonds. Such obtained hydrogenated amorphous silicon has a sufficiently low amount of defects, and it can be used to make devices such as solar photovoltaic cells. It is used as solar cell material with a varying and wider band gap up to 1.9 eV. The absorption coefficient of amorphous silicon hydrogenated is very high. It can be deposited by sputtering CVD or plasma enhanced CVDs. Can be deposited on a variety of substrates such as plastic, metal, etc., and therefore very useful in different types of device fabrication. Now we come to group 4-6 compound elements, that is lead sulfide, lead selenide and lead telluride. These are important compounds in this group. These compounds are characterized by narrow energy gaps, high energy mobilities and high dielectric constants. They have energy band gap as low as 0.5 eV. The band gap is very low for these materials. The unique feature of the direct energy gap in these compounds is that its energy band gap increases with increasing the temperature, which means the energy gap has a positive temperature coefficient. Main application of these compounds are in light emitting devices, diode lasers and detectors in the infrared spectral region. The next important class is 3-5 elements. We have in this class we have like from group 3 we have aluminum, gallium, indium, and group 5 elements which are nitrogen, phosphorus, arsenic, antimony. So this if you combine all these with these things you get 12 prospective combinations, and the most important ones are gallium arsenide, indium phosphide, gallium phosphide, and gallium nitride. 10 commonly used compounds are listed in the next slide by of these 3-5 element. All these 3-5 combinations crystallize either in the diamond lattice like silicon or germanium, and if the atoms are different, we call as zinc blende structure. And if similar kind of structure is where you have one atom and another atom is at a particular distance, and that structure, if it is hexagonal, if it is FCC, in that case this is either diamond structure or zinc blende structure. But if it is with the hexagonal lattice, then it is called as Woodside structure. So these are some of the compounds: gallium phosphide, aluminum arsenide, aluminum antimonide, gallium nitride, gallium phosphide, gallium arsenide, gallium antimonide, indium phosphide, indium arsenide, and indium antimonide. Another type of components are important group 2 and group 6 compounds. Semiconductors, these are zinc oxide, zinc sulfide, zinc selenide, zinc telluride, cadmium sulfide, cadmium selenide, and cadmium telluride. So this is group 2 and this is group 6. So if you combine these, you get some of the important compounds. See, all the 7 2,6 materials have wider band gap ranging from 1.5 to 3.6 electron volts. Actually, you can have you can just get an idea of the difference between all these kind of semiconductors. These have various common applications like LED, signal processing. The growth methods vary by material, most commonly grown by melt growth. Other than zinc oxide and zinc sulfide, this cannot be grown by melt methods. So all these can be grown by epitaxial methods. Advantages: less energy lost, more efficient and potential for lower cost. Higher breakdown voltages, so higher power and frequency applications. If they are having higher breakdown voltage, obviously they can be used for higher power and at a higher frequency applications. Then because of higher doping concentrations, we have thinner device layers and higher electron mobility in these materials. It gives you a faster device operation. Now this is the tellurium. And it is this is the you can say picture of the melting point is 400 nearly 450 degrees centigrade. The boiling point is 988. The band gap is very low, 0.38 electron volt. So if you see at room temperature, it will it behaves like almost like a conductor, and electrical resistivity is 1.1 10 to the power minus 4 ohm meter. Density is 6.24 gram per centimeter cube. Thermal conductivity is this. Thermal expansion is this, and atomic number is 52. The crystal structure where it crystallizes is trigonal. Because of its low electronegativity, tellurium form a variety of materials with the small band gaps and find applications in photoconducting materials, solar cells, infrared detectors, and production. Most of the tellurium is obtained from copper deposits where it occurs in trace amounts. And this is ternary and quaternary compounds. In addition, we have some important ternary and quaternary compounds which are very important for device applications point of view. So this, as we saw, it is actually in binary compound. You add the third one with a certain fraction. So the fraction of this is you can say atoms for this element are replaced by this. So you have such compounds: aluminium, indium arsenide, gallium arsenic phosphide, gallium indium nitride, gallium indium arsenide, gallium indium phosphide, aluminum gallium arsenic antimonide, so gallium indium arsenic phosphide, and aluminium indium arsenide. See, this for these all these materials, you can just have a look and just read the details. So you have an idea of all the possible semiconducting materials. I think this with this we come to end to this lecture. If you have any doubt, any question, you can ask me. Well, if there are no questions, then thank you. See you in the next class. We will see. We'll try to cover the remaining portion of this section. Thank you.